Recording. Hello everybody, welcome back. This is homework 2, part 2C. So we're going to be implementing Broyden's method with step size adjustment and inversion to Jacobian as necessary when progress is slow. So like secant and Newton methods from the last videos, Broyden's method is another way to find roots. We'll just pull up Wikipedia here. In numerical analysis, Broyden's method is a quasi-Newton method for finding roots in k variables. So if you remember from the last video, we did this Newton's method for k variables in k functions, and we were able to return the roots of that function using Newton's method. But this actually consisted of doing this inversion of the Jacobian. Now, if we're going to use the inversion of the Jacobian every iteration of our function, it takes a lot of time, a lot of processing power, and it's something that's not always attractive to do, to calculate, especially more roots for more complex functions. So what this guy Broyden is saying, if I scroll down a little bit, what we can do is we can actually directly update the inverse of the Jacobian matrix. And if you can see here, this is using the Sherman-Morrison formula. The inverse of the Jacobian, if we have like a guess of the Jacobian, we update it so our result is equal to our initial guess plus all of this here. Now, it kind of looks like a big mess, and we'll actually code this all into Python. But basically what we want to do is utilize this in order to find the roots without taking the inverse of the Jacobian matrix every single iteration. So I'm going to start by defining Broyden. And what we're going to need for Broyden is we're going to need a function, an initial guess, max iterations, 50, and a tolerance. Oop, got a colon there. Okay, now what we need is we need an initial guess for our Jacobian. Now, I'm not exactly sure what to guess for this, so we can say f Jacobian equals, what we'll use is np.I, which is an identity matrix, and it will be the size of our initial guess. And then we need an initial guess for our inverse Jacobian, so call it f jac inv inverse, and that's going to be equal to, we'll just say it's equal to the Jacobian, which of course it's not, but this is just going to be an initial guess, just a way to start off our iterations. Now it's going to be set up a lot like this Newton's method function up here. So again, we're just going to be saying the function value equals the function at our initial guess, so x 0. And then what we want to say is for I in range max iter, we basically want to do what we did up here, what we did up above in Newton's method, so x1 equals x0 minus, and instead of doing this jmp.linearalgebra.inverse, instead of taking the inverse of this Jacobian, we're just going to use this f jac inverse, which is our guess. Matrix multiplication with f0, and then we'll have our new f1 equals, enter, f1 equals f at x1. And then, just like up above, if JNP dot linear algebra dot norm of F1 is less than the tolerance we break. Otherwise, what we're going to do is we're going to have this, well, if we pull up Broyden's method real quick, what we need is a delta xn, which is going to be our change in x, and we need this delta fn, which is our change in function value. So I'm going to call this dx for the change in x values, and that's going to be equal to x1 minus x0. And then, of course, df is going to be equal to f1 minus f0. And then we're going to set our new x0 equal to x1 and our new f0 equal to f1. Okay, so this is basically what we have up here for Newton's method. Now the difference with Broyden's method is that we actually have to implement this updating the Jacobian, or the inverse of the Jacobian matrix. So I'm going to need to code this into Python. And the way I think I'm going to do that, I'll split up my screen here. So we have that there. Okay. So what I basically just want to do is copy this into here. And what we're going to say is, so f jac inverse. So the new Jacobian inverse, actually I'm just going to copy this because we're going to be typing this a lot. So it's going to be equal to the current inverse of the Jacobian plus, and this is going to be dx minus the inverse of the Jacobian, matrix multiplication with df, which we can see right here. And then this all is going to be matrix multiplied with this xn, delta xn t, which is the transpose. So dx dot t, that's the transpose, matrix multiplied with the inverse of the Jacobian. And this is all going to be divided by the transpose again, dx dot t, matrix multiplication with the inverse Jacobian, matrix multiplication with the df. And then what we want to do is return, I believe we want to return x1, which is just like what we did in Newton's method. Okay, and now what I'm going to do is call the function. This should be Broyden. I'm going to use, this has to be capital F. We're going to use this fun, which is this function up, excuse me, this fun up here, which is a function we borrowed from scipy.optimize.root. So we're going to use that. Then we need an initial guess, so x0 equals, and I think we want to use an array of zeros. So we'll just say 0 is our initial guess. So we'll run that, and actually what we end up getting is this nan. And what this means is infinity. And actually I think I think a good way to look at this is if I print, so we'll print the current I value, just say I plus 1. And then I think we want to print x1. Right, so if we look at this, what is this doing? I mean, we can see here that our values are just heading up into infinity, and we reach infinity and we just keep going. And I think the reason why this is, I'm gonna make this full screen again. If we look back here at homework 2, we want to use step size adjustment. So we want to be able to control the step size we're taking. So the way I want to do that is I want to have basically a statement here that says while, and then we want to make sure the value of f1 is not getting bigger than the value of f0. So the way we can do that is by looking at this value here, the norm of f1. So while the norm of f1 is greater than the norm of f0, some room there. What I want to do is implement this this variable called n, which n will control our step size, the step size that we're taking. So in order to do that, the first thing that I have to do is I have to come up here. So this line here. If we look down here at dx equals x1 minus x0, so change in x. So if I were to subtract x0, this would be x1 minus x0, that's dx. So we're going to rewrite this using dx. And then I can write, we can basically say x1 equals x0 plus dx. So now we are basically defining dx to be our step size. Now I can come down here and say that n, well, we'll define n up here as being equal to 1. So now we'll come down here and we'll basically say that n equals, so if f1, if the norm of f1 is larger than the norm of f0, then n will now equal 75% of our original n. So we'll basically be taking a step that's 75% the size of our full step. So we will not be taking a full step anymore. And then we can say x1 equals, just like above, x0 plus dx, but this time it will be times n. That takes into account our step. And then we need to redefine f1 equals f of x1. Look at this real quick. Okay, and now it looks like we're getting pretty... So if I look back up here, these are the values we should expect. 0.84 and 0.16-ish. So if I look back down here, it almost looks like we pass it up a little bit, but not exactly. We're kind of around our value, and then all of a sudden it just shoots up to infinity. So what I'm going to do is I'm also going to print the n value here. Maybe that will give us some insight into what's going on. Okay, so it looks like we have problems when our n value gets really small. 10 to the negative 7, 10 to the negative 8. So we want to be able to fix this problem of n getting too small. And the way we can do that is by using inversion of the Jacobian as necessary. Now, if you remember from the beginning of this video, I explained the reason why Broyden's method is useful is because we don't need to calculate the inversion of the Jacobian every iteration. So it seems a bit silly to purposely use the inversion of the Jacobian and calculate that. But in this case, calculating the inversion maybe once or twice is going to be a lot. It's going to be necessary in order for us to actually use Broyden's method, and you doing it once or twice is not going to be nearly as bad as doing it many times, or every iteration like we did in Newton's method. So the way we're going to do this, we want to set up a statement. So where we do this n value here. So what I want to say here. So if our n value, we want to be looking at this n value. If n is less than, we want to give it a lower limit, let's say 1 times 10 to the negative 10th, then we need to basically do the inversion of the Jacobian. So the way I want to do this is, first I'm going to get rid of this identity matrix as our initial Jacobian guess, and I'm just going to say that when we call the function, we're actually going to specify an f jack. So we're actually going to specify the Jacobian when we call this function. And then we're actually going to calculate the inverse, and that's going to be equal to the p dot linear algebra dot inverse of f jack at our initial guess. So that's going to be our Jacobian, and that's going to be our inverse Jacobian that we get when we specify the Jacobian when we actually call the function Broyden. And then from there, we can come down here. So if n is too small, what we want to do is we want to calculate the inverse of our current Jacobian. So just copy this. So we want to have a new Jacobian inverse, and what that's going to be is the np dot linear algebra dot inverse of our current f jack at our current x 0 point. So this is going to be the inverse of our current. It's going to be the inverse of the Jacobian we're currently using on the specific iteration. So it's going to be different than this f jack inverse up here, because this is within the iterations. And then from here we can calculate a new dx. And we're going to be calculating it the same exact way as this. So just copy and paste that. Okay, run that. Let's see here. So we're actually, when we call Broyden, we're going to need to specify the Jacobian. So f jack equals, we need to specify what that is. So we need to get the Jacobian of our function. So we'll call it fun jack. The Jacobian of our function is equal to, we'll use the jacks dot Jacobian. Jacks dot Jacobian of fun. And that should give us the Jacobian. So then our f jack will equal to function underscore Jacobian. See what we get here. Let's see. Is this what I'm looking for? We call the function dx is equal to, it's a little hard to read when it's spaced out so much. Jack's dot Jacobian, yeah. F jack. But is this what I'm expecting to get? It still looks like it gets too small. Fun Jacobian fun. So we have this while, and then if n is less than 1 times 10 to the negative 10th, we get the new Jacobian inverse, which is equal to the inverse f jack. Why is this not doing what I want it to do? Huh. This is interesting. I feel like what happens if I decrease my tolerance? Doesn't do anything. Maybe if I just delete some lines here, it'll be easier to read. It's greater than 0.75. Maybe if I wonder what happens if I decrease that. But actually, this is the answer. If I look up here, 0.8412, 0.8412, 0.159, 0.159. So this, it's found the answer, but it keeps going for some reason. But why does it keep going? A, to decrease the tolerance. Oh, okay. There we have it. So decreasing the tolerance caused it to break correctly. So it looks like, just again, right here we have 0.84 and 0.16. Comparing it to Newton's method, which we did before, we get the same roots of 0.84 and 0.16. So using Broyden's method with step size adjustment, which we did with this n, we used n to control the step size, and the inversion of the Jacobian as necessary, which we used the inversion of the Jacobian here. We were able to implement Broyden's method and calculate the roots of this function, wherever it is, right here. So yeah, thank you for watching, and I will see you in the next video.